Hi again, everybody. Welcome back. We've been talking about kinetic energy of rolling objects, and we just recently defined how you can have linear kinetic energy. All right, that is K. I've been calling it KL. That's our 1/2 mv squared. But it also has rotational kinetic energy, and we call that. Or I've been calling it KR. In fact, I'm not going to write it there. I'm going to write it next to it. K sub R, rotational kinetic energy, which is 1/2 I, of course that's our moment of inertia, times the angular velocity squared. Okay, and so whatever kinetic energy it has total is going to be the sum of those two kinetic energies. So with this problem right here, this is really just sort of a conceptual problem because we don't really have any other values to put in, but we can predict which of these two round objects reaches the bottom of the ramp first. In fact, let me do something here, real quick here. I'm going to shrink this down like so. Oops, nope, not like that, like that. Okay. All right, so initially, where both of these, well, here's a hoop right here, and here like an open cylinder, and here's a closed cylinder or a disc. What energy do they both have at the top right there? Well, the initial energy, I'm going to do this in blue. The energy initial for both of those is going to be mgh, right? It's got potential energy. It's each of the masses, which by the way are the same, times gravity times the height h, because they're at the top of the ramp. Now I realize that if you look at these two masses, they don't look like the same mass. I mean, it looks like this is a lot less massive than this right here. But it tells us that they are the same mass and also the same radius. So what must be true right here is that all this, maybe this hoop right here it's thicker, it's wider than this. Maybe this disc right here is pretty skinny thickness-wise. All right, so with this hoop, all the mass is concentrated around the edge, around the radius, whereas here all the mass is kind of distributed from the radius towards the center. So it's more centrally located than it is on the hoop. Okay? So, which will reach the bottom of the incline first? Well, I'll do energy final hoop and then energy final of the, what are we going to call that? The disc D for disc. Okay? Well, first of all, when they reach the bottom of the ramp right there, do they have any more potential energy? No. All right? Potential energy is gone because it is no longer has any height. But what kind of energy does it have? It has kinetic energy. Kinetic energy of the hoop and kinetic energy of the disc right there. Well, that kinetic energy of the disc, this right here, is made up of those two types of kinetic energy, linear kinetic energy and rotational kinetic energy. All right, so that means it's going to be, hope I can fit all this in, 1/2 m of the disc times velocity of the disc squared plus 1/2 moment of inertia of the disc times rotational velocity of the disc squared as well. Okay? We're going to do the same thing. Oh, I've been writing disc, haven't I? Darn it, that is, I apologize, that's the hoop. That is the hoop. Doggone it, I'm just going to have to erase those and then try again. Mass of the hoop times velocity of the hoop squared. My bad. And then moment of inertia times rotational velocity of the hoop squared. Okay, that's the hoop on top. The disc is the same thing. Now we're going to put a D. We're going to have md times velocity of the d squared plus 1/2 moment of inertia of the disc times angular velocity of the disc squared right there. All right, now here at this point we're going to need to look and refer to our table to tell us what the moment of inertia is for each of those objects. I'm going to write this below right here. We're going to say the moment of inertia of the hoop, all right, and the moment of inertia of the disc, and this will help us to predict what which is going to reach the bottom first. Okay. So let's flip back over to our previous page right here. Remember we had this whole table set up where it was, in fact, you know, I'm going to see if I can delete some of this stuff right here. Can't remember how to do that. Delete. Oh, that's going to take forever to do it individually like that. Well, oh, there we go. Gone. Okay. No, now they're back. What is going on? Yeah, it might just take forever. So, try it one more time here. I'll at least delete all the writing for the disk and for the hoop right here, so we can see what's going on. There we go. Okay, these first two, we've got a hoop or a cylindrical shell, and we've got a disk right here. And so our hoop is going to be our moment of inertia is mr squared. Let's go ahead and write that at the bottom. All right. For the hoop is simply mr squared right there. And so for the disk, the solid disk, that is going to be, ooh, didn't mean to do that either. I meant to do this. 1/2 mr squared, right? 1/2 mr squared. So let's write that in. So 1/2 mr squared. So which has a greater moment of inertia? Well, it's going to be the hoop right here. Think about it. All the mass is concentrated around the edge. Here, all the mass is distributed from the edge towards the center, and so you've got a lot more of this mass at a closer radius to the axis of rotation than the hoop does right here. So, long story short, we can say the moment of inertia for the hoop is going to be greater than the moment of inertia for the disk. And that isn't our final answer, but it should help us to find our final answer. If this right here, let's see, let's do a different color. If that is going to be greater than this right here, and they both have the same initial energy, then that means the linear kinetic energy, so of the hoop, oh, I'm still writing in red. Oh, it's red and blue again. The linear kinetic energy of the hoop is going to be KLH, sorry. Linear kinetic energy of the hoop, and the linear kinetic energy of the disk. The disk is going to have greater linear kinetic energy than the hoop. You see what I'm saying here? If this right here, the moment of inertia right here of the hoop is greater than this, then that means if the rotational kinetic energy of the hoop is greater than that of the disk, then that means it's going to have a lesser linear kinetic energy. So the kinetic energy of the hoop is going to have to be less than that of the disk, which means, this is what we're really solving for right here, the final velocity of the hoop is going to have to be less than that of the disk. Meaning that the disk is going to reach the bottom of the ramp first. The disk will win. All right, because we have to figure out what the total, well, they both have the same total amount of kinetic energy, but the hoop has greater rotational kinetic energy because of a greater moment of inertia. The disk has less. So therefore, the disk has to have greater linear kinetic energy, therefore a faster top speed, and therefore it'll reach the bottom of the ramp first. So that's kind of our logic, our rationale for solving these types of problems. They both start with the same initial energy. They have the same final energy, but the energy is distributed in different ways because each of the two masses has mass distributed in different ways. So that's example 1014. I'm going to stop right there, I believe, but be sure to pick up on the next one. And thanks for following along, and make sure you ask me if you have any questions. See you on the next one.